Okay, welcome back. So we're going to pick up where we left off from the last lecture. We'll resume lesson 1. So this will be lesson 1 continued. So from the last lecture, I gave you a 6-step procedure for graphing rational functions. So why don't we start off with another example of graphing a rational function. So let me identify one. Let's say y, which is equal to f of x, which is equal to let's let our p of x equal to x squared minus 4. So let me type that in, x squared minus 4, and we'll let our denominator q of x equal to x squared minus 1. So x squared minus 1. All right, so the objective, of course, is to graph this function. So what do we do first? Well, the first thing we do is we check for symmetry. So sim check. So we start off by evaluating what is f of negative x. So that would be negative x quantity squared minus 4 divided by negative x quantity squared minus 1. And when we simplify that, we get what? X squared minus 4 divided by x squared minus 1, which happens to equal to f of x. So what does this mean? This means that f of x has even symmetry. F of x even symmetry. And I'll use the letters S, Y, M, M as a shorthand for symmetry. Okay, so good, symmetry. What do we do next? Next we hunt for vertical asymptotes. So vertical asymptotes, and those are found after canceling common factors in the numerator and the denominator by setting the denominator equal to 0. Okay, what's left of the denominator equals 0? Well, the denominator is equal to x squared minus 1, and it has no common factors with the numerator, so we just solve this, and we note that we have 2 vertical asymptotes for this. X equals negative 1 and x equals to 1. So we'll have 2 vertical asymptotes. Horizontal asymptotes, what about them? Do we have any? We most certainly do. And why is that? Because the degree of p of x is what? Looks to me like it's 2. And that also happens to be the degree of q of x, which is 2. So that is the signal that we have in horizontal asymptote. And what is that? Well, since the degrees are equal, by rule, the line y equals 1 is a horizontal asymptote, and it's found by taking the ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator, which is 1. Okay, intercepts. So what are the intercepts? Well, we can find the y-intercept by setting x equals 0 in the numerator or just setting x equals 0 in the function, and when that happens, if we plug in x equals 0, the output would be 4. So 0, 4 is the y-intercept of this function. And how about the x-intercepts? Well, we have to solve what? X squared. So the x-intercepts are found by setting x squared minus 4 equals to 0. And almost by inspection, we can ascertain that negative 2, 0 is an x-intercept, and 2, 0 is an x-intercept. All right, looking good. Okay, and what next? Okay, then we need to determine where the graph is above and below the x-axis. All right, so that's where we construct our table of signs. So that would be let's say, we'll start off with a 5 by 5 table. All right. Okay, so here's our table, and let me drag it out of the way here. Okay, and so remember what we put in the first column? We put the prime factors. So here we'll have, okay, so we'll have x plus 2, x minus 2, then we'll have x plus 1, and then we'll have x minus 1, and then in the last cell of the first column, we'll have our function. Next, we draw the real number line. Okay, here's our x-axis. And then on the x-axis, we plot the zeros of each of the prime factors. So we have a 0 at -2, and -2 is in the domain, so we make this a solid line. Then we have a -1. -1 is not in the domain, so we have a dashed line, dashed vertical line as a column separator. Then we have 1. 1 is not in the domain, so again we have a dashed line as a column separator. And then we have the last 0, which is 2. And 2 is in the domain of the function, so solid line. And it looks like I need another column, so let me just go ahead and extend this table out one more column. Okay, so now we go and we start filling in the signs, right? So if we choose a number between -infinity, that's a -infinity, and -2, and we plug it into each of the factors, we'll essentially have a negative number. And so a product and a quotient of 4 negative numbers is always positive. So between -infinity and -2, the graph is above the x-axis. All right, so next interval, between -2 and -1, this factor has a positive sign, this factor has a negative sign, this factor has a negative sign, this factor has a negative sign. So a product of a positive and a negative number is negative. A negative number divided by a positive number determined by the product of these two numbers would be a negative number. So between -2 and -1, the graph should be below the x-axis. All right, between -1 and 1, what happens? Well, if you take any number between -1 and 1 and plug it into this factor, you'll be positive. You'll be negative for this factor. You'll be positive for this factor, and negative for this factor, right? Choose any number between -1 and 1, plug it into this factor, ascertain the sign, and you'll notice it's negative. And so we have 2 negatives participating in the construction of the function, and so that means between -1 and 1, the graph is above the x-axis. How about between 1 and 2? Well, between 1 and 2, this is a positive factor. This is still a negative factor. This is a positive factor. And this is a positive factor. So between 1 and 2, we have an odd number of negatives in the mix of the function. So that makes for a negative output of the function. And so ergo, it would be below the x-axis on this interval from 1 to 2. And then finally, when x is greater than 2, everybody's positive. And so when x is greater than 2, the whole function will be above the x-axis. So that means we are ready to graph this function, all right? And it turns out I have a ready-made graph set up for you. So let me copy that. So here would be the sketch, and I'll explain the sketch. So here we have, oops, sorry, didn't mean to put that mark there. Let me erase that. Put back on pointer and drag it a little bit. Let me extend this, extend the page, and drag the graph down. Okay, so let's explain what's going on here. So between -infinity and -2, let me highlight that region of the x-axis, or that segment of the x-axis. Between -2 between negative infinity and negative 2 as promised. Here's my origin right here. Here's my y-axis, my x-axis. As promised, the graph is above the x-axis, and it's also asymptotic with right here. Look here. Here's my horizontal asymptote, y equals negative 1. So this portion right here conforms to our expectations. Now between negative 2, see, between negative 2 right here and, where was negative 1? Negative 1 is right here, right? Between negative 2 and negative 1, we should be below the x-axis. See, here's negative 2, here's negative 1, right there. And so, see the branch right here? It's below the x-axis, and it's also asymptotic with right here. Our vertical asymptote x equals negative 1. So this branch conforms to that piece. Okay, so now note also that negative 2, 0 is an x-intercept, 2, 0 is an x-intercept. And we also had the y-intercept as being at 0, 4 from previous work, right? See right here? 0, 4 is the y-intercept. Okay, so what happens between negative 1 and 1? Well, look, we're above the x-axis. And we also have to be asymptotic with these two vertical asymptotes, right? And so this is the only kind of curve that meets the criteria. It hits 0, 4, and it's asymptotic with the vertical asymptotes, and it's above the x-axis. We can't, this would be wrong, right? If we drew it this way, why would this be wrong? Because if we drew it this way, then ultimately we would fall below the x-axis on this interval, and that can't happen. Okay, so we're constrained to only draw it this way. All right, and then a similar explanation goes for this piece of the branch. Okay, so I have a question for you. So where is f of x increasing? On what interval is f of x increasing? So identify the intervals where we have this criteria, where f is an increasing function. Well, remember what an increasing function is. When x increases, y correspondingly increases. And so that would happen here, right? That happens here. So we're increasing there. Are we increasing anyplace else? Well, sure. It looks like this branch. Note that as x increases, y increases as well. So the blue denotes the regions where x is increasing. All right, now let's consider the case where f is decreasing. Purple. Well, remember what the concept of a decreasing function is. When x increases, y decreases like that. Okay? And so where does that happen? Well, that happens here, right? Because as x increases, y correspondingly decreases. And it also happens here, too, on this branch. So there's some of the dynamics of the graph. Okay, so that wasn't so bad. Another example. Let's do another example, another graph. Next page. So I'd like to graph the function that shows up in calculus a lot, this function. Show you how to graph a function involving absolute value. Consider this. G of x is equal to 3x plus the absolute value of x divided by x. All right. Now, the strategy for graphing functions that have absolute values in them, in their specifications, is to reformulate g of x into an equation that does not involve absolute value. All right, and so when this happens, you're probably going to end up with a piecewise defined specification for g of x. So recall that absolute value of x. Remember from last lecture that absolute value of x is defined piecewise. It's equal to x if x is greater than 0, or negative x if x is less than 0. And we make use of this definition to replace this absolute value of x with an equation that does not involve absolute value. So the strategy in dealing with equations that involve absolute value is to reformulate them into equations that do not involve absolute value. So if we were to do this, what we'll get is g of x is equal to, here's how it works. It's going to be piecewise defined, 3x plus x over x if x is greater than 0. Now note that x can't be 0 for this function, right? Because if x were 0, we would be dividing by 0, and of course that would be absurd. So that means, what do we have? So that 3x plus x is 4x, 4x over x is 4. So if x is greater than 0, then g of x is simply 4. All right, now what happens if x is less than 0? So if x is less than 0, then the absolute value of x is replaced by a negative x, right? So it would be 3x plus a negative x over x if x less than 0. And that effectively equals to what? 3x minus x is 2x, 2x over x is 2, so it's 2. All right. So what would the graph look like? Well, the graph would look something like this. I need a graph, wizard, Cartesian, next, finish. So let me extend the page. Oops. Grab this and drag it down. A little bit further. Okay, so if x is greater than 0, the function would be 4. Now, at 0, we have basically what's called a discontinuity. So what I'm going to do is I'm going to draw an open circle like this at 0, 4. Okay, so at 0, 4 we have an open circle. That means the function is not defined at x equals 0, but for x greater than 0, the output of the function is 4. So we have this open ray for x greater than 0. And then for x less than 0, okay, we'll have an open circle at x equals 0, y equals 2, and for x less than 0, the output is 2. So this would be our graph. And I'll leave it to you to use the online graphing calculator to verify that this is, in fact, the graph of this function. All right, next topic is I want to talk about functional composition. Composition of functions. Everybody's favorite topic, I'm sure. All right, so if I'm given two functions, f of x and g of x, so given two functions, we define the composition of two functions using this notation. Actually, there are a couple of symbols for it. So we have f composed with g of x. Okay, and that's equal to f of g of x. And it's really, interestingly enough, a very simple matter. The way we compose functions is we just say, we take the outer function, which in this case is f, okay, take f of x, and then, okay, I'm going to draw this long vertical bar, and this is called an evaluation bar, and then we just, wherever we see x and f of x, just replace it with g of x. Okay, that's all it means. Nothing more, nothing less. Okay. One of the tricky things, though, about composition of functions regards the domain of a composition of functions. So let's talk about the domain of a composition of functions before I give you an example. So the domain of a composition, okay, it goes like this. It consists of the values. Okay, it consists of consists of g of x values that are in the domain of f of x. In the domain of f of x. Let me write that. Okay. So in other words, g of x could have values that are not necessarily in the domain of f of x. Okay, so you need to identify g of x values that may not be in the domain of f of x, or as a matter of fact are not in the domain of f of x, and exclude those from your declaration for the domain of the composition. Okay, not only does it consist of g of x values that are in the domain of f of x, but it also consists of x values that are in the domain of G. Okay, so you have to be careful when you specify the domain of a composition that are in domain of G. Okay, because it's effectively almost kind of like an intersection of two sets, but not quite an intersection. So let me give you an example of a composition. Let's do a rather sophisticated one. Next page. All right, so let me let f of x equal to x squared plus x minus 2 divided by x minus 3. Okay, and let me let g of x equal to x squared minus 4 divided by x squared minus 1. Oops, sorry. Got my pen backwards on that one. Try it again. X squared minus 4 divided by x squared minus 1. Okay, so what we want to calculate then is f composed with g. Okay, and so the rule is, very simply put, this would equal to wherever we see an x in f of x, we just replace the x's, which I'm circling in red here, just replace all of those circled x's with g of x. Okay, so this would be, well, let me go ahead and write it in black, just for consistency's sake. This would simply be g of x squared plus g of x minus 2 divided by g of x minus 3. Okay, and of course we'll have to simplify that, and I'll do that in just a second. But before we proceed, let's talk about the domain of the composition. All right. So the domain of the composition would be the set of values of x that are permitted for this new function. Obviously, it'll be the set x such that well, x can't be 1 nor negative 1. Remember, in the composition, we have to exclude values of x that are not in the domain of g of x. So x can't be 1, and x can't be negative 1. right? So we have that as restrictions for the domain. Where else? Okay, also we have this consideration. Okay, that can't, what I've circled in green can't be 0. So g of x cannot be 3. Okay, so that's another thing. So you'll have to solve this equation, x squared minus 4 divided by x squared minus 1 equals to 3. So whatever values of x you find by solving this equality, you'll have to stick in here as omitted values of x for the domain. Okay, so I guess we could attempt to solve this, so we can cross multiply, right? So x squared minus 4 is equal to 3x squared minus 3. And so we have 0 is equal to 2x squared plus 1. And so that yields complex values. Okay, so actually there are no real solutions for this. It appears that there are no real solutions for this. So no real solutions. So we're off the hook on this. Okay, so we got lucky. This may not always be the case. So this is our domain. See, this has no real solutions. You can't take the square root of negative numbers yet, since we're only talking about real numbers. All right, so now we can go ahead and complete evaluating our composition. So let's go ahead and simplify this expression right here. So let me see. See if I can copy. I don't know if I can copy. All right. Well, anyhow, I'll go ahead and continue. So f composed with g of x is equal to, well, let's see, we need g of x squared. So that would be, right, g of x, which is x squared minus 4, divided by x squared minus 1. And we take that quantity, and we have to square it. Then we have to add g of x again. So that would be x squared minus 4 divided by x squared minus 1. And then we have to subtract 2. That would be our numerator. And then we have to divide all of this by what? G of x minus 3, which would be x squared minus 4 divided by x squared minus 1 minus 3. All right. So next page. So where does that leave us? Okay, so when I complete the square of g of x, so g of x squared turns out is x to the 4th minus 8x squared plus 16 divided by x to the 4th x to the 4th minus 2x squared plus 1 plus, okay, and then we had x squared minus 4 divided by x squared minus 1 minus 2, okay, and then that was divided by x squared minus 4 divided by x squared minus 1 minus 3. And now we have to simplify that. All right, so what I'll do is I will go ahead and multiply upstairs and downstairs by this term right here. So I'll multiply upstairs and downstairs by that term. And so what I get is x to the fourth minus 8x squared plus 16 plus x to the x squared minus 4 times x squared minus 1 minus 2 times x to the fourth minus 2x squared plus 1. And of course, in all of this divided by what? That would be x squared minus 4 times x squared minus 1. Okay, minus 3 times x to the fourth minus 2x squared plus 1. All right, so we still have a little bit of ways to go to simplify this function. And so this would be x to the fourth minus 8x squared plus 16 plus x to the fourth minus 5x squared minus 5x squared plus 4 minus 2x to the fourth minus 2x to the fourth plus 4x squared. Try not to repeat myself. Minus 2. And then all of this divided by x to the fourth minus 5x squared plus 4 minus 3x to the fourth plus 6x squared minus 3. So now we can simplify that. And so that's equal to minus 9x squared plus 18 divided by negative 2x to the fourth plus x squared plus 1, with restrictions that x cannot equal to negative 1 and x cannot equal to 1. Okay, so there's your composition. And of course, yeah, g of x cannot equal to 3. All right, so a quick whirlwind tour of composition of functions. Another topic that we may deal with during this term would be the difference quotient of functions. So the difference quotient, something that you probably had in algebra. And if you go on to calculus, this is something that you'll probably use in every class of your calculus class. Okay, so the difference quotient, if I'm given f of x, okay, so its difference quotient would be represented as f of x plus h minus f of x divided by h. So that's all we have to know about a difference quotient. So for instance, if I give you f of x is equal to, say, x squared minus 2x plus 1. X squared minus 2x plus 1. So what is the difference quotient? So difference quotient would be x plus h quantity squared minus 2 times x plus h plus 1. Perhaps I should type this out. This is looking a little bit messy here. So let me go ahead and type it out. I think I can type it out. Use a text editor. So difference quotient of f. That would be x plus h quantity squared minus 2 times x plus h plus 1. Okay, so that would be the numerator. And we take all of this and we divide it by h. Okay, and so that would equal to x squared plus 2xh plus h squared. Oops, I'm sorry, I missed a term, didn't I? So this would be f of x plus h. I forgot to subtract off f of x, right? That would be x squared minus 2x. I beg your pardon. I always do that a lot. Okay, so f of x plus h minus f of x. Okay, and then we take all of that and we divide it by h. Sorry about that. Okay, so there's our difference quotient. And so we'll simplify it. So that's equal to x squared plus 2xh plus h squared minus 2x minus 2h plus 1 minus x squared plus 2x minus 1. And we take all of that and we divide it by h. So simplifying the numerator, that would equal to, well, the x squares cancel. We're left with 2xh plus h squared. It should be a minus 1, sorry. Plus h squared. Looks like the 2x's cancel. Minus 2h. Minus 2h. And the 1's will cancel. And we divide by h. Okay, looking good. So this would equal to 2x plus h minus 2. All right, so this is our difference quotient for this quadratic. All right. So later on when we talk about trig functions, trigonometric functions, we'll be calculating difference quotients for them as well. All right, next topic. The next topic we'll talk about will be one-to-one functions. Next page. Next topic, next page. Okay, so let's talk about one-to-one functions. All right, we say f of x is 1-to-1, and I'll be lazy, I'll write it as 1-1, if f of a is equal to f of b, if and only if a is equal to b. Okay. So why are we concerned about one-to-one functions? Well, one-to-one functions are particularly important in trigonometry because we like to find inverses. Okay, So let's do an example. Show so back to the equation editor. Show f of x, which is equal to 1 divided by x minus 3 minus 7. Okay, so here we have our show that this function is 1-to-1. So how do we do that? Well, here's how. Use the definition. So I'll go ahead and handwrite it. So 1 over a minus 3 minus 7 is equal to 1 over b minus 3 minus 7 if and only if what? 1 over a minus 3 is equal to 1 over b minus 3. It's a b minus 3. If and only if b minus 3, I'll take the reciprocals of both sides of the equation. B minus 3 is equal to a minus 3. If and only if b is equal to a. Okay? So if b is equal to a, then we can backtrack going in the opposite direction of this chain of reasoning and get that we have this relationship. And this relationship matches the requirements for 1-to-1. All right, so let's do another example. Let's try and find the inverse of a rational function, of another rational function. So find the inverse of f of x. And let me give you f of x. So let's let f of x equal to another rational function. I like rational functions, don't I? Let's make it 1 minus x divided by 1 plus x. All right. So do you remember the procedure for finding the inverse of a function? Well, you replace f of x with y. So replace f of x with y. Here's the procedure for finding the rational function. The next thing you want to do is interchange x and y in the equation. So interchange x and y. So x is equal to 1 minus y over 1 plus y. And then when you do that, solve for y. So let's solve for y. So we have x, I'm going to cross multiply, x times 1 plus y is equal to 1 minus y. And so from there we get x plus xy is equal to 1 minus y. And now I'll get all my y's on the left-hand side, so I'll have y plus xy. And I'll take this x and I'll move it to the right-hand side. It's equal to minus x plus 1. Now, next I'll factor out my y here. So I'll have y times 1 plus x is equal to 1 minus x. Now we can solve for y by dividing both sides by 1 plus x. Now this is kind of a quirky function, isn't it? Because if we look at, before I make my comment, one last step. Once you solve for y, replace y with the inverse notation. So f inverse of x is equal to 1 minus x over 1 plus x. Now this symbol right here, this is not the reciprocal of f of x. This symbol is actually means the inverse of f of x. Okay, now back to my comment. Here is our original function right here. And here is our inverse. They're the same, interestingly enough. This isn't always the case. It just so happened that I got lucky that the function and its inverse are the same function. Okay, so as a matter of fact, that's comparatively rare when this happens. So what is it about inverses that are interesting? Well, it turns out that a function composed with its inverse, okay, a function composed with its inverse is the argument of the function, which in this case is x. And this is a means of checking. So how do we know that this is the inverse of the function? Well, let's check. If we compose f with f inverse of x, we should get x. So we know that f of x is equal to 1 minus x over 1 plus x. All right, so f composed with f inverse is equal to 1 minus f inverse of x divided by 1 plus f inverse of x. Now substitute in our calculations for f inverse of x. And so that's equal to 1 minus x divided by 1 plus x. And then we divide all of that by 1 plus 1 minus x over 1 plus x. And we simplify. So after simplification, we should get x. So I'm going to multiply upstairs and downstairs by 1 plus x. So we'll have 1 plus x minus 1 minus x quantity divided by 1 plus x plus 1 minus x. And so that's equal to 2x divided by 2, which is equal to x. So that's one nice property about functions and their inverses. When you take their compositions, you get the argument back out. All right, so functions and their inverses. Okay, so next topic. Let's talk about functions and their transformations with respect to graphing. So transformations of functions. I want to sketch the graph of this and talk about some transformations on a particular function. So let's say we have a function f of x is equal to x squared minus 4. Okay, so that's obviously a parabola that points up, and the vertex is at the origin. Now let's change the let's spice it up a little bit. How about we talk about the graph of the absolute value of this? Okay. So what is this? What is this all about? Let me see. Is that the right problem I wanted to deal with? No, as a matter of fact, I wanted to make it. That's not the function I wanted to talk about. I wanted to make it point downward. So let's say f of x. Let's start off with f of x equals to minus x plus 4. Okay, so that means its graph, the graph of this function is going to be, it's going to have a vertex at 0, 4, right? So if x is 0, y is 4, and then it'll have x-intercepts at 2 and negative 2. So this would be the graph. Now I'll go back to spicing it up. So let's suppose we want to graph the absolute value of negative x squared plus 4. So what does that mean? Well, remember, whenever we take the absolute value of something, the result is either 0 or positive. So what's going to happen when we take the absolute value of this graph is, you see this portion of the graph right here that's below the x-axis? This is my x-axis right here. Well, that's going to be reflected back above the x-axis, and you're going to have these little branches that are going to look like this. So that would be a modification to the graph when you do the absolute value. All right, so let me draw you a picture, and we'll talk about some transformations. Or let me install a picture here. Let me hunt for one. Yeah, here we go. So let me create one that I've got ready-made here. Stand by 1 second. So I'm going to select this graph right here. Copy. And I'm going to paste it right here. Okay, so now, all right, so what's going on here? Okay, so the graph of the absolute value of x squared plus 4 is shown in green. So let me accentuate that here. It'll be this piece right here. So here we go. So here is, oops, sorry, I got a little bit off track here. Go back to my green pen. So this is the absolute value of negative x squared plus 4. Note that since we're taking the absolute value, it will never drop below the x-axis. So one of the things I want to talk about is the notion of a vertical stretch. So let's consider another function, and this will be a transformation. Let's consider f of x is equal to 3 times, let me erase this. F of x is equal to 3 times negative x squared plus 4. So how does that affect the graph? Well, with this 3 multiplier now, it means that for the original values of x, the outputs now are multiplied by 3. And the effect is it's going to do a vertical stretch of the graph. And so instead of, for instance, the original, if we have this point 0, 4, well, if we multiply 4 by 3, it's going to stretch it out to 12 in the vertical direction. And so this orange graph that you see here, this orange graph, let me accentuate it, see if I can pull up an orange color. Yeah. So this orange graph is an example of a vertical stretch when we multiplied the original function by 3. So these things happen. And basically, in trigonometry, we do this a lot more than we do and than we have done in algebra. Okay, there's going to be a considerable amount of work going on in trig doing this. All right. Likewise, if we were to multiply, okay, so so now that you've got this, let me go ahead and erase this because it's getting kind of congested here. All right, so what would happen if we were to take our output and multiply it by 1/2? So instead of stretching it, we kind of shrink it, or kind of, yeah, we do basically a vertical shrink of the function. So basically amounts to a vertical shrink. So let me erase this. So how about we use a multiplier of 1/2? So it basically multiplies all the output values by 1/2. And which representative curve would that be? That would be essentially the blue curve. Let's see, would that be the blue curve? Let me check. Actually, I think it would be, yeah, this blue curve right here. So this would be a vertical shrink. Notice that this local maximum at 0.4 got shrunk down to 0.2. So this point got shrunk to here, okay? So there's an example of a vertical shrink. Now, we did this all, in, of course, in the y direction, the up-down direction. We can also do this in the left-right, the x direction. So how would we modify f of x to account for horizontal stretching and shrinking? So here's how. Let me erase this. So an example of a horizontal stretch would be something like this. Or actually, this would be an example of a horizontal shrink. So if I were to take the original function, f of x, which is shown in red, and multiply x by a number greater than 1, we would have essentially, effectively, a horizontal shrink. Okay? So if I were to do something like this, how would that affect the output of the graph? Well, what I'm doing here is I'm dividing all of the x's by 3. And so that would basically compress the graph. So I'm compressing the graph. And what would be that? That would be an example of the purple graph. Okay, so it would be this. This would be a horizontal shrink right here. See how the x-intercepts are moved closer to the origin? Okay, but it still has the same y-intercept, but the graph is compressed. It's like somebody took it on both ends and just squeezed it together. Okay, so that would be a horizontal shrink. Now, so conversely, we would have a horizontal stretch, okay? And horizontal stretch basically is tantamount to multiplying all the x's by a quantity. So if we change the 3 to, say, a third, so let's do that. So let's go x, we'll divide our x's by 3 in the function definition, but this is basically amounting to multiplying all of the x's by 3. And what this does is it will stretch the graph in the x direction. So this is kind of a review of one of the topics you had from algebra, when you were graphing functions in algebra, and the black curve right here. Notice that the x-intercepts move off the original curve from -2 to -6. So we basically multiplied all the x values by 3. So this is an example of a horizontal stretch. All x's are multiplied by 3 here. And in the equation, we divide the x inputs by 3, and the effect is to multiply all the input values by 3. Okay, here, this is it right here. Okay, and so for instance, yeah, you can check that. So these are all examples of function transformations. Okay, horizontal, vertical transformations. Please, 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 please pay very particular attention to this segment of the lecture, because we will be doing this quite a lot when we start graphing trigonometric functions. Trigonometric functions are totally built on horizontal shrinking and stretching and vertical shrinking and stretching. And I'll try to give you as many examples as time allows. All right, so let's move on to the next topic. And let's talk about absolute value again. Some more notes on absolute values, solving equations with absolute values. Okay, so do you remember how to solve something like this? An absolute value that's less than a quantity, say like this. Do you remember the rules? How do we solve for x? Okay, so the rule is we wedge, remember we have to convert this problem into one without absolute value. And so this is basically amounts to replacing 2x plus 3, solving 2x plus 3 greater than -6 and less than 6. That's the rule for solving an absolute value that's less than the number. And so when we solve this, we'll have -9 less than 2x less than 3. And divide all sides of the inequality by 2 to isolate x. So we have -9 halves is less than x is less than 3 halves. Okay, so that's one inequality. Okay, so how about if we have an absolute value being greater than an absolute value? So something like this. Do you remember the procedure for solving something like this from your algebra? Absolute value of x plus 2 is greater than the absolute value of x plus 1. Do you remember what the rule is? Okay, well, the rule is we replace the absolute value using its square root definition. So basically, we transform the problem into one without absolute value. So using the definition of absolute value, we have this. So absolute value of x plus 2 can be reformulated as the square root of x plus 2 quantity squared, and that must be greater than the square root of x plus 1 quantity squared. And then okay, so to complete this, we go ahead and square both sides of the inequality. So we have x plus 2 squared must be greater than x plus 1 squared. Okay, and then we go ahead and complete the squares. So x squared plus 4x. Oops, that doesn't look like a 4, does it? Sorry about that. Let me fix that. So x squared plus 4x plus 4 must be greater than x squared plus 2x plus 1. Now we solve for x, so we have 2x is greater than -3, so x is greater than -3 halves. All right, so that's our solution. Okay, so that's one example of absolute value. So another example is when we have the absolute value of a quantity greater than a number. So for instance, let's consider 2x minus 31. I'm sorry, 2x minus 3 absolute value is greater than 5. All right, so to solve this, without using absolute values, we do it piecewise. We first say that 2x minus 3 is less than -5. We solve this, and then we union this result with 2x minus 3 is greater than 5. And so you solve the two inequalities and union them together. All right, so let's see another example. Let's see here. Let me check. Okay. Okay, so let's reformulate or rewrite this function, the absolute value of x minus 2 minus the absolute value of x plus 1 as a function without absolute value. All right? Okay, so we encounter what? We encounter what are called corner points, right? So you may recall from algebra, we have corner points. So the way we deal with this is we leverage our definitions of absolute value. So recall, absolute value of x plus 2 is equal to x minus 2 when x minus 2 is greater than 0. Greater than or equal to 0, that is. All right? And it's equal to negative x plus 2 when x minus 2 is less than 0. Okay, so x minus 2 greater than 0, that's the same as saying, what, x greater than or equal to 2, right? So we can go ahead and simplify this inequality here. And x minus 2 less than 0, that's the same as saying x less than 2. So we'll make those annotations. And do the same thing. Do the same thing for the absolute value of x plus 1. So absolute value of x plus 1 is equal to x plus 1 when x plus 1 is greater than or equal to 0, or x is greater than negative 1, greater than or equal to negative 1, and it's equal to negative x minus 1 when x plus 1 is less than 0, or x is less than negative 1. All right, so now we have corner points at x equals 2 and x equals to 1. So now, to reformulate the function into one without absolute value, we have to consider intervals where x is less than negative 1, where x is between negative 1 and 2, and where x is greater than 2. So here's what we do. All right, so we have the absolute value of x minus 2 minus the absolute value of x plus 1 is equal to, now when x is less than negative 1, when x is less than negative 1, x is also less than 2, right? So this would equal to negative x plus 2 minus what? Minus, let's see, what was the original function that I had? Yeah, minus minus x minus 1 for x less than negative 1. Okay, and then you can, of course, simplify this. All right, now when x is between negative 1 and 2, okay, x is less than 2, so this would be negative x plus 2. But now x is greater than negative 1, so that would be minus x plus 1. And so this happens on this interval. And of course, when x is greater than 2, what do we get? So this would be x minus 2. I'm sorry, erase. Minus x plus 1 for x greater than 2. Okay, and so knowing this information, you can graph it, right? So it's possible to graph the function. So let's simplify this. So this would be 3 for x less than negative 1, minus 2x plus 1 when x is between negative 1 and 2. And it would be minus 3 for x greater than 3, right? So our graph would look like this. Here's my graph. The graph didn't show. Well, try it again. Graph. Hello, graph. Math, graph wizard, Cartesian, next, finish. So not showing my graph. I'm not seeing my graph. It must be a, here we go. Drew it up here for some reason. Okay. Drew a whole bunch of them, didn't it? Let's see. Let me delete this. I wasn't aware that it was drawing them up here at the top of the page. Okay, so I'll just freestyle the graph drawing then. So our graph would be something like this. So here's -1. Here's 2. It's my x-axis. So for x less than -1, our output would be 3. This would be 3 right here. Between -1 and 2, let's see. It'll be this straight line right there, and then right here. So it's going to look like that. And so you can see why -1 and 2 are called corner points, because what happens at corner points? You get a corner in the graph, obviously, right? Okay, so right there. All right. Okay, so the next topic and the final topic for our review of algebraic structures would be circles. So circles. All right, so let's talk about circles. So the equation of a circle is this. The general equation, or the standard form. I guess they call this standard form or generalized. I think it's standard. The standard form of the equation of a circle. It doesn't really matter. I'll fix it later. I'll look it up later. Okay, is this where the center, okay, C is the center, is at HK. And radius is equal to R. Okay, so everybody knows what a circle is. All right, so, and then in circles, we have what are called quadrants. So very important notion in trigonometry. Note that this is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. So in our XY plane. And so say I ask you to graph this equation. So let's graph 2x squared. Well, let me use the equation editor. It looks cleaner. So 2x squared plus 2y squared plus 4x plus 3y is equal to 3. So if I give you this equation, you should be able to recognize that this is the equation of a circle, and you should be able to identify the radius as well as the center and then sketch it in the XY plane. So how do we know how to compute the center? Well, we compute the center by completing the square on x. So we have 2x squared plus 4x. So do you remember how to complete the square from the last lecture notes? We do it by factoring out the coefficient on x. So this would be 2 times x squared plus 2x. Okay. And then we take 1/2 the coefficient on x, which is 2. So 1/2 of 2 is 1. And then we square the 1. So we have 1. So what we've done is we've added 2 to our equation. So the right-hand side would be 3 plus 2. Okay, and then we complete the square on the y terms. So our y terms are 2y squared. Plus 3y, right? Okay, so we factor out the 2, the leading coefficient. So it'd be 3 has y. All right, and then we take 1/2 the coefficient on y, which is 3/4, and we square it. So 3/4 squared is 9/16. And then we add, 18/16 to both sides. Okay, so that would be 3 plus 2 plus 18/16, right? All right, and then we'll just put it all together. So the equation of our circle then is let me check. Two times x plus 1 quantity squared plus 2 times y plus 3/4 quantity squared that's equal to what? 98/16, right? Because 5 plus 18/16 is, let me check. 5 is 80/16, so that would be 98/16. Now to put it in a representative form where we can graph it, we can divide both sides of the equation by 2. And so we have x plus 1 quantity squared plus y plus 3/4 quantity squared is equal to 98/32. So what is the center of our circle? Well, the center would be -1, -3/4. And the radius would be equal to the square root of 98/32, which is equal to 7/4. Okay, so there's your radius. And then from there we can sketch. So -1, -3/4 would be roughly right there. And then, so we can go 1 3/4 this way, and then 1 3/4 this way, and then 1 3/4 this way, and then 1 3/4 this way. So those 4 points would define our circle, and then we can just connect it as best we can in the circle. Okay. All right, so there's our circle drawn. Okay, so there we have it. And we'll talk more about this as the class goes on. All right, so now that ends our algebraic review for this class. So at some point, you need to start working on your WebAssign assignments that are on the schedule. So what are those? Let's pull that up and take a look at what our WebAssign expectations are. Let me insert internet browser and pull up the class website. Let's see if we have any. I can't recall what our WebAssign obligations are. Okay, so if we go to the WebAssign schedule, looks like we should be doing assignment number 1, and that's due on the 28th for this particular section. And then we'll have a test on Chapter 1 as well, forthcoming. That will be available in WebAssign. So we'll talk more about this in class for the summer. This should be summer 2014, right? Summer 2014, so I need to fix this. Summer 2014. Okay, so make note of that. Okay, so that's it for lesson 1, or review of algebra.